In this video, we're going to look at potential energy diagrams and explore how to interpret and draw them. We're going to start with the potential energy diagram for an exothermic reaction. So this is the combustion of methane. And I've drawn here what's happening during this reaction. So we have our reactants, we have methane and 2 oxygen molecules, and we have our products, 1 carbon dioxide and 2 water molecules. And during this reaction, what has to happen is the bonds in the reactants, so our oxygen double bonds, as well as our carbon-hydrogen single bonds, all of these bonds have to break. In order to break bonds, we have to add energy. So here you see this is the energy that's required to break the chemical bonds. This achieves a higher state of energy. So we have all of our elements, their bonds are broken. This is an activated complex where the atoms are rearranged, but we don't have new bonds formed yet. This is the highest energy state of the reaction. Once we've rearranged our atoms and are ready to form new bonds, this can occur. And when new bonds form, energy is released. So on the left here, we have the energy required to break the bonds in our reactants. And on the right, we have the energy that's released when the bonds in our products form. The difference between these two energies is the enthalpy of the reaction. So if we were to find the energy that's required to form, or the energy that's released when the bonds form, and subtract the energy required to break bonds, we would get this reaction. Now this is an exothermic reaction, and we know this because our reactants have more potential energy than our products. And so when this reaction occurs, there's going to be a net release of energy to the surroundings, and our delta H value will be negative. We can simplify this diagram as shown on the right here. So on the right, we have our potential energy diagram. In this diagram, we have our reactants on the left and our products on the right. The difference in the potential energy of our reactants and our products is going to be our enthalpy of reaction. We still have our activated complex at the highest energy level, but this time we've just rounded out that curve. And so we call the energy that's required to start at reactants and go to form our activated complex our activation energy. So this is the energy barrier that is required to be overcome for a reaction to occur. So the activation energy of our forward reaction, so that's starting at our reactants and going to our products, is smaller than the activation energy of our reverse reaction in this case. And the difference between these two activation energies is going to give us our enthalpy. So if we take the activation energy of our forward reaction and we subtract the activation energy of our reverse reaction, so our forward reaction minus our reverse reaction, we get the enthalpy of the reaction. And so this allows us to solve for the energy required to break bonds or the energy released when bonds form if we know 2 of the 3 pieces of information. We're now going to look at an endothermic reaction. So this reaction is the decomposition of ammonia. So 2 ammonia molecules decompose into its elements, so 1 nitrogen molecule and 3 hydrogen molecules. And I've drawn the molecules here. So in the reactants, we have 2 ammonia molecules. In our products, we have 1 nitrogen and 3 hydrogen molecules. So once again, in order for this reaction to occur, we first have to break the bonds in our reactants. So we're going to be breaking 3 nitrogen-hydrogen bonds. Breaking bonds requires an input of energy. So to go from our reactants to our activated complex, there's going to be a net gain in energy. In our activated complex, the bonds in our reactants have broken and our atoms begin to rearrange. This is the highest energy state of the reaction. Once we've rearranged our atoms, we can form new bonds. And once again, there's a release of energy when bonds are formed. And so what we have here is our reactants are the lower potential energy than our products. And so our overall enthalpy for this reaction is going to be positive, because more energy is needed to break the bonds in our reactants than we get back when bonds form in our products. So once again, we can simplify this diagram. And so here we have the potential energy diagram where we have our reactants on the left, our products on the right, and you'll notice the balanced reaction. We have this increase in energy from breaking bonds and then a decrease in energy from forming bonds. So at the very top of this graph, we have our activated complex. And the energy that's required to go from the reactants to the activated complex, that is the activation energy of our forward reaction. And the energy that's required to go from our products to the activated complex is the activation energy of the reverse reaction. And the difference between those 2 values is going to be our delta H value. So once again, the activation energy of the forward reaction minus the activation energy of the reverse reaction equals our enthalpy of reaction. And so we can see in our endothermic reaction, we have this uphill climb to go from reactants to products. And so our products have more potential energy than our reactants.